Okay, so here's where we were last time. We were looking at setting up a triple integral over a sphere. This sphere in particular, and notice this sphere is not centered at the origin. The center is way up here, right? Some distance a directly above the origin, and then radius a so that it's kind of sitting on top of the origin there. Okay, so we've talked through most of the problem last time, and this is one little tiny little bit that we need to clean up. So just a reminder where we're going with this. Theta cross sections look like that, right? And you can see here that these theta cross sections, well, they go, all the way around. So the range of values of theta is 0 to 2 pi. Right? On a given value of theta, on a given theta slice, here's that theta slice again. Now we're just looking at it sort of head on. Makes things easier to see. Phi starts at 0. And then these phi slices, keep in mind they emanate from the origin. Phi is measured from the origin, not from the center of whatever you might happen to be looking at or whatever else might be convenient, right? Sadly, always from the origin. That last slice happens here where phi is pi over 2. So there's our range of values of phi, 0 to pi over 2. So again, we talked through all that last time. Okay, lastly now, on our phi slice of our theta slice. So looking at this thing here, we want to talk now about what's the range of values of rho. Okay, so rho starts there and ends there. So what does that mean, though? How am I going to find rho at these points? Well, just keep in mind what we're looking at here is a theta slice of our original solid. Let's go back and look at this picture. We're talking about points there, and then on our phi slice up to here. So we're talking about actual points on the surface of the sphere. This one, you can see right there, it's at the origin. Rho is 0. That's a freebie. Okay. And this other one, well, that's not at the origin, but I can see geometric information about that point. That point is on my sphere. So in order to understand what rho is at this point, I simply need to understand the spherical equation for this sphere and solve for rho, and that rho is what I'm looking for. That's the upper bound for our rho range. Okay, so let's find the equation of this sphere. Here's the rectangular equation, algebra 2. Right. Remember, it's centered above the origin by a distance a, has radius a. Right? And then just like we did way back, early in the class, chapter 1 or 2, wherever this is, multiply it out and plug in the conversion formulas for spherical coordinates. So x is blah blah blah, y is blah blah blah. Stick that all in there, multiply it out. Look for convenient opportunities to save yourself a bunch of trouble. X squared plus y squared plus z squared is rho squared. That's handy. It's nice, right? Of course, this a squared cancels with that a squared. And you can see how the rest of the algebra plays out. Nice punchline. Here's rho. Right? That then is our upper bound. I should do this in purple. But this is the value of rho at this point. That is the upper bound for as rho moves along that phi slice of that theta slice, and you can see that in the final integral here. So as previously discussed, theta goes from 0 to 2 pi. Phi on a theta slice goes from 0 to pi over 2, and rho on a phi slice of the theta slice goes from 0 to 2a cosine phi. Okay. All right, our original integrand, while we're here, original integrand was that, rho squared. Don't forget your stretching factor. Again, probably the most common thing for students to forget. It's one of the most important things and also one of the most forgotten things. Don't forget to stick that. If you're going to do integrals in a different coordinate system, you are doing change of variables. You've got to stick in the stretching factor for change of variables. Conveniently, given a coordinate system, it's always the same formula. for change of variable stretching factor. And so just memorize it, but just make sure don't forget to stick it in there. Okay. All right. So altogether, then your integrand is rho to the fourth sine phi, which is not that bad. In fact, that's pretty straightforward. Okay. All right. So done with that section now. While I'm thinking about it, let's see here. Today is Thursday. Don't forget we have an exam on Monday. Summer terms move blindingly fast, right? Feels like we just finished the last exam. So there's exam on Monday. Today is the cutoff material for the course. So it's a fair game material for the course. There's going to be everything up through and including what we do today, which should be, let's see, this is section 5.8. It should be 5.8 and 5.9. Possibly 5.10. We'll see. These are fairly short sections, so we'll see what happens. Anyway, okay. So I'll send y'all an email tomorrow, later this afternoon about that. Okay, so here is our new problem that we want to consider. Suppose I want to compute the mass on this bent rod, like that. It's bent around in space. And now here's a point of view that you could take, I suppose. You could say, well, this is just a really odd-shaped three-dimensional solid. And you could chop perpendicular to the x, y, and z axes and make it work. But that would be a nightmare. Look what a weird shape that is, right? Oh, my gosh, it's just unthinkable. Because that's not how we describe things that are bent around in space. The way we understand how things are bent around in space is we think of them as following a curve. We're going to think of this rod, even though technically it's three-dimensional, we're going to think of it as being kind of, in effect, for all practical purposes, one-dimensional. Very practical. Here's some silly examples, by the way. If you go to Home Depot and buy chain or cable or something like that, they will talk about the mass density of the cable or the chain, not in terms of mass per unit volume. Nobody cares about the mass per unit volume of it. I'm going to be using it by the length. They will give you mass per unit length of the chain. They're going to pretend like this chain is effectively a curve, right? Likewise, that's how you pay for it. You pay for it by the foot. You don't pay for it by the pound, right? Or by the, can you imagine buying stuff by the cubic inch? I don't even know how they do that. Okay, so we're going to think of this now in a different way. Forget about thinking of this as a solid. I want to think of this as being a curve, right? And we want to understand how to take some clearly accumulation problem, right? I mean, mass accumulates. If I chop this rod up into little pieces, the mass is the sum of the little pieces of mass. But it's accumulating from our new point of view now. It's not accumulating over a solid. It's accumulating over a curve in space. We don't have such a construction, right? We have triple integrals, which accumulate over solids, three-dimensional solids in space. No such thing yet for accumulating over curves in space. Okay. All right. So let's talk about how to do this, and it's not that surprising. It's chop it up, add it up. Same strategy that we did for single variable integrals, double integrals, triple integrals. We're going to do the same thing here. It's just the chop it up looks a little different. Right? There's that curve, and I can chop that up into little pieces. You know, like so. And then look at the mass on each one of those little pieces, and then add up those individual pieces of mass, for example. Okay, on each little piece, now let's draw our attention to this one little piece here. Look at that one little piece. This is a little bit too small to deal with, so just for sort of visual purposes, I'm going to magnify. Let's look at that one little piece as, you know, blown up like that. And on that little piece, I need to know how long it is. Right, the length of that little piece, and I need to multiply by the mass per unit length to get the mass on that piece. Well, hey, hang on. What is the mass per unit length? Mass per unit length may depend on where you are on the rod. it may depend on location. So I'm going to have to compute mass per unit length in terms of location. So where is this little piece of rod located? Right? And now the idea, which point do I pick, that point or do I pick that point? Well, of course, we're going to take a limit. These are going to get increasingly small. Round-off errors are going to go away. Let's not worry about that. Okay. All right. So with this setup arranged, here's the kind of constructions that we're going to be doing. And now, I've been phrasing this from the point of view of let's compute the mass of something, but it could apply in other circumstances. I'm going to show you another application of this construction in a minute here. But let's, for the moment, think about this in terms of mass. On each little piece, mass per unit length measured at that point, describing where that little piece is. Mass per unit length times length gives you how much mass there is in that little piece. I'm then going to add that up over the whole curve. So there's your formula. Being as this is a chop it up, add it up, I'm going to call this an integral. Okay. This is not a single variable integral exactly. It's certainly not a Calc 1 integral. So it's an integral that's happening over a curve. And for, I guess, historical reasons, this gets that's a little bit sloppy by today's standards use of the word line, but this is going to be thought of as a integral over a, think of line as just, like a drawing. So this gets called a line integral. By the way, I put the little prefix over here. I call this a scalar line integral for reasons that I can't give you details on just yet, other than it turns out there's other kinds of line integrals. So this one, I'm just going to call it a scalar line integral to draw attention to the fact that we're talking about an integrand, which is a scalar valued, a real valued function. Okay. Other kinds of line integrals we'll talk about later. Okay, notation. Again, we're going to rip off notation that we've used in the past, right? In this Riemann sum that we're talking about, we're multiplying by little pieces of length, delta S, and we're going to abbreviate that exactly as you would guess, ds. Now, I emphasize that is not dx or dy or dz. So, how to compute this? Whole separate question. We'll get to how to compute it in a moment, right? But that's how we're going to denote that. This summation is happening over the curve, so again, hopefully no surprise, an integral symbol saying we're adding up over that curve. You've got to indicate as a subscript what your domain is over which you're adding all these things up. So there's your notation. This is a scalar line integral defined by that expression. Okay. Everybody happy before we move along? How to compute it is, again, very non-trivial question. Before we get into computations, though, I think it's instructive, as we've done with all other integrals we've defined. Before we get all excited about computing them, let's see how the Riemann sum specifically applies to applications, right? Keep in mind there's always these three phases. Turn an application into a Riemann sum. That's step one. Then there's the question of how to turn the Riemann sum maybe into something that you can compute with, fundamental theorem or something like that. Fingers crossed, right? But that you got to make that first connection between the application and the Riemann sum. Okay, so other than the mass example, which I'll go ahead and point to here, bent rod has a non-constant density given by some function. On each little piece, mass is density times length. The total mass is the sum of all the little pieces of mass, thus giving you that line integral. You'll notice I'm using integral notation instead of Riemann sum notation. That's just notation. That's just this kind of a shorthand for these kinds of expressions. Okay. All right, but let's see now here a different example, and I think this is a fun one. So I thought of this example when I was renting a house that was kind of out in the woods, sort of, and that was an interesting experience, by the way. But it was on a large plot of land. The driveway was really long. It was several hundred yards long driveway. right? And it was all curved and stuff going through the woods. And it occurred to me, oh my gosh, if that driveway were to get a bunch of snow to fall on it, and if I had to shovel that driveway, oh my gosh, how much snow would I have to shovel, and would I be physically capable of this task? Again, it's one thing to shovel a driveway that's 50 feet long or 60 feet long, but if your driveway is 500 feet long, wow. Okay, so what we've got then to solve this problem is we have a curve. Right? And yeah, sure, the driveway's got a thickness. It's technically an area. Yeah, sure. Right. But that's not how people talk about driveways, right? We talk about driveways as, well, it follows a certain path. Right? Think of it as a line. It's a line which, one of the parameters of interest that as relates to that line is, thickness. At a certain point along the line. Okay. So what I would like to do is let's again consider a scenario where it's snowed, and so here's the snowfall, and I'm going to exaggerate just for sort of emphasis, geometric sort of visualizing. Here's the snow that has fallen on that road, not to scale. Let's hope. And notice I've drawn it as being thicker, deeper over there, and less deep over there. Right? And that's not too surprising. Wind does funny things with how snow accumulates. Right? Trees mess it up. So suppose we have some function that describes the snow depth across this plot of land, and then we have this curve moving across the plot of land that is the driveway. Okay. All right. So with that in mind, what I want to do is I'm going to compute the total amount of snow. Right? There's all this snow. Oh gosh, I wanted to be in the highlighter mode. There's all this snow that has accumulated, across the driveway here. How would I add up how much snow that is? Well, we're going to take our curve and chop it up into little pieces. That curve, moving along like that, we're going to focus our attention on one little bit of that curve. A little piece of curve of size ds, delta s if you prefer, but we're using integral shorthand. And, well, how much snow do I have there? Okay, well, this is just a matter of writing it down, and the length of that little piece of driveway is ds. The width of the driveway there, well, that's some constant. Look at the statement of the question. What is it, like 8 feet or something? Let's see here. I'm just calling it W. Yeah, but maybe it's 8 feet. Whatever, the point is it's in there. And then I've got to multiply that by height. Well, again, the height is some value. Right, here's the snow sitting over that piece of the driveway, and this h is known. It is a function of location x and y. So, how much snow you got? Well, the amount of snow that you have is this. We've got a little rectangular box of snow, and it is, let's see here. Oh, color choices. H times W times ds. So that's how much snow there is on each little piece, and we just want to add up on each little piece W times H times ds. And so there's a line integral. Right, so the way I would actually answer this question, if I were, thankfully it never did give me any, I didn't have to shovel any snow, so, close one. But if I did want to compute how much snow I was about to shovel or had shoveled, there's an integral that'll do it. Everybody on board? Okay. So, how are we going to compute these things? It's all well and good to take some application and develop a fancy notation for it. As of the moment, that's all I've really done is I've developed a fancy notation. How do we compute these things? Well, we're going to take a strategy that we have already used and apply it to this new context. Let me remind y'all, change of variables. Why did we even start doing change of variables? It's because we had domains that we didn't like. The domains were bumpy and wiggly, or the domains had corners, or something about the domain was undesirable. And the big selling point for change of variables is you can take your domain, this bad domain, and view it as an image of something, pull back through that change of variables function, and your new integral is an integral on the pullback domain. Right? So the foot in the door there is find a way of viewing your undesirable domain as an image. Well, here's my undesirable domain. I've got some curve moving through R2 or R3. Just for fun, I'm drawing it here in R3. The snow example was a curve in R2. Whatever. And I need to view this curve as being an image of something. An image of a more desirable domain over here. And good news, we know how to make curves images. That's parameterization. Been there, done that. Right? So step one, parameterize your curve, and then we're just going to follow the pattern that we've done before of trying to figure out how then do I pull back the integral defined on this purple bent curve. How am I going to pull that back through the parameterization and get an integral, a nicer integral defined here on our interval on the t-axis, and which, by the way, awesome, right? We love this domain, an interval on the t-axis. Calc 1, right? We're good if we can do this pullback. Okay. Alrighty. Do that there. Okay, so here's an example, by the way, of a parameterization. If you're parameterizing a circle, for example. Okay. All right. So having parameterized, we would chop up this interval in the usual way. Chopping up the pullback domain would effectively give us a chopping up of our parameterized curve. And I just need to know how big is that stretched out piece of parameterized curve in comparison to how big is that little piece of the t-axis. So we're looking again for our stretching factor. When I apply this parameterization, this thing goes over and has that image. It's not going to be the same size, probably. How much bigger is, by what factor has its length been changed? Yeah? Right? Everybody see how this is morally identical to what we did with change of variables. Different details. Okay. So, I need to compute this ds and hope, fingers crossed, that it is a conveniently evident multiple of dt. And that's what's going to happen. So here's how that calculation goes down. What I'm going to do is I'm going to point out that the vectors are easier to understand than little pieces of curve. This is what we've done in the past. It's easy to understand vectors. We have formulas for things involving vectors. And we have a derivative transformation that allows me to take an input vector and get the corresponding output vector. Right, so this is what I'm going to do. I'm going to say, look, as you move along this little piece of the domain, the change in the domain is E1 dt. E1 because, well, there's only one standard basis vector. It's, I could just call this dt, I suppose, right? But I'm calling it E1 dt because I want to emphasize that that is a vector. It's to be thought of as a vector and not to be thought of as just a number. Okay. The corresponding output, this dx vector we've talked about in the past. The relationship between the dx vector that comes out and the E1 dt vector that goes in, the derivative transformation. Right? That's what the derivative transformation does. It takes input changes and gives you output changes. Okay, so let's see that calculation then. Here it is. to figure out this output vector dx and how that comes from this input vector e1 dt. The derivative transformation is the thing that does that job. Now we just have to compute. Good news, dt is a scalar. It factors right out. Right? Cool. That's how scalars work in linear transformations. What's left, we're applying the derivative transformation to, I'm going to say, a standard basis vector, which is going to make you think partial derivatives, but keep in mind there is only one input standard basis vector. There is only one input variable. So that what we're accustomed to calling a partial derivative, well, it's the only derivative. It's just x prime. And so we get this nice result that dx is v dt. And more to the point, of course, and what we're interested in about dx, what I really need to know about dx is its length, ds. That was I need to know how long that is. How long is that little piece of curve? So the magnitude of dx is going to be what I'm looking for. So let's take the magnitude then of this dx. Oh, I color-coded that wrong. My dx, I'm going to take its magnitude to get ds. And there you go. Nice, simple formula. ds is an evident factor times dt. This is our stretching factor. It's the magnitude of the velocity vector. Magnitude of the derivative, speed of the parameterization, which, by the way, once you make the realization that what we just wrote down was distance equals speed times time, this whole exercise in sophisticated derivative transformation stuff seems, making a mountain out of a molehill. Right? I keep this calculation in here, though, because this is not the last time that we're going to be relating input vectors and output vectors. And I think seeing this in how the derivative transformation plays a role, I think, is really valuable. Okay. All right. Okay, so there you go. There's our stretching factor. Magnitude of the velocity vector. And from that, we can just write down how to do integrals. Here it is. This is our theorem for how to compute scalar line integrals. If you want to compute this scalar line integral, parameterize and pull back. Parameterization means we're going to just, plug in how x is a function of t. We're going to compute ds in terms of t by sticking in the stretching factor. And as required, we've done the pullback. This integral over a curve has now been pulled back, and now it's just an interval on the t-axis from a to b. This is a good old Calc 1 single variable integral. And we're really good at computing those. So, that's all there is to it. Let's do some examples. Let's suppose let's go back to our bent rod, non-constant density. And let's see, it's going over a curved path, which is the top half of the unit circle in R2. So let's draw that picture real quick. So our curve is, let's see here, I'll use red, fine. It is this. There's our curve. We know, by the way, that the very first thing we have to do is parameterize. Keep in mind the parameterization is basically playing the role of your change of variables function. You can see it right here in the formula, by the way. The parameterization is how you do the pullback. You rewrite x in terms of the parameterization. You get your stretching factor as the magnitude of the derivative of the parameterization. It's all about the parameterization. So parameterize first. It's easy to parameterize this half circle. Cosine t sine t. We all remember how to parameterize a circle. Right? By the way, I guess I'll make an observation. If maybe you're a little it's been a while, right? I mean, done a lot of stuff since then, but if you're a little shaky on parameterizations, now would be a really good time to go back and polish off those skills. Parameterizations are going to be a really big deal moving forward. We're going to be parameterizing lots of stuff. When we get into Chapter 6, pretty soon, parameterizing is a big deal. Okay, so there's your parameterization, and then let's see here. Now, on that parameterized curve, we've got mass. The mass is described by density as a function of x. Here is that formula for density as a function of location. We've already argued that over this curve that we just parameterized, over that curve we want to do an integral of that density function. Right, so we've got a line integral. Line integrals compute mass because mass accumulates over the curve, right, as previously discussed. And so here we go. We want to compute that line integral. We've got our parameterization. This formula says we need the magnitude of the velocity vector as our stretching factor. So let's crank that out. So magnitude of the velocity vector. Now you got to make sure you remember all your formulas for derivatives, etc. But this one works out really nicely, and the magnitude is just 1. Lucky break. Of course, you should not expect that this lucky break will happen most of the time. Okay. And now we're just going to pull back through the parameterization. So here we go. Let's see here. Our parameterization, x, was given as a function of t like that. There's our parameterization. Right? Density as a function of x. Well, let's find that formula. The density was given as, here it is, x squared plus 2y squared. So x squared plus 2y squared is this. So there I've pulled back the original integrand through the parameterization. Now let's think about the ds. So ds, of course, this ds right here is stretching factor times dt. We've computed our stretching factor here. Stretching factor is 1. Conveniently, I get to just kind of toss aside as a factor. And we are left with then this single variable integral, which is just a matter of cranking it out. Now again, I have to remind y'all, Calc 2 is prerequisite to this course. I expect and assume that you are proficient with all the standard integration techniques. This one's going to require, well, this one's most conveniently done with something called a half-angle formula. Half-angle formulas are from trig long ago. It's prerequisite to prerequisite to prerequisite to this course, right? But it keeps being useful. My standard quip about why trig is useful is trig comes from circles and the world is full of circles. It just is, right? So this kind of thing is going to keep coming up. So make sure you're good with all your trig. Half-angle formulas are that little bit of trig that makes this integral work out nicely. Okay. How we doing? Everybody happy? There's another example in here. I'm going to let y'all read through this example on your own. This goes back to the whole, snow thing, and it's just a matter of details. But this is a good example to read. Unfortunately, this one does result in an integral that's not particularly tractable. But in real life, if I had shoveled hundreds of yards of snow, I would need to know exactly how much snow that was so I could brag about it. I mean, right? Of course, right? So I would go to the trouble of taking this integral, even if it's not tractable, and I would do some sort of numerical, take Simpson's rule or left-hand approximation. You all remember all that stuff, right? And this is something that you can certainly get an estimate from, and if you're just estimating, that's plenty good enough. Okay. All right. Bunch of examples for you all to wade through. Our next new kind of integral, not that different from what we just did. We're going to define something called a surface integral. And the analogy is very strong. This time, instead of having mass following a one-dimensional curve through space, here I'm going to imagine that we are following a two-dimensional surface through space. So maybe you have a bent sheet of metal kind of a deal, right? Or something along those lines. Or maybe this is a part of a hill, and you're trying to keep track of how many certain kind of insect that lives on this hill. And the insects, there's fewer insects at the higher altitudes, and there's more insects at the lower altitudes. And how many insects are there? And you got to keep in mind that where the land is angled, there's a lot of land in some sense there, right? Anyway, the point is, if you want to do an accumulation over a surface instead of over a curve, here's what's largely the same as with line integrals. Chop it up, add it up. Dimensionally awkward, though, right? I mean, this is living in three-dimensional space, but I'm not chopping it up into pieces of volume, so I can't use a triple integral. And even though I'm chopping it up into little pieces of area, this is not, right off the bat anyway, a double integral, right? Because a double integral just takes place in the xy plane, and this is very importantly not in the xy plane. So all of these features, the dimensional awkwardness, the way that this doesn't really fit in with any of our existing integrals, just like with scalar line integrals. Okay, so chop it up, add it up, though. If I'm computing mass on that little piece of surface, or if I'm counting insects on that little piece of surface, what have you, right? I'm going to be multiplying some, quantity per unit area, some sort of a density function. I'm going to be multiplying by area on each of these pieces. Okay. So I'm going to need to know the area of that little piece. That's going to be a challenge for us to figure out. If you have a piece of area that's floating up in space, how much area is that? It's importantly, it's angled, right? It may be turned in some weird way. So we're going to have to figure that out, how to compute that area. Once I do, though, I just need to multiply by the density. Density has to be computed at some point, right? And with those things identified, with area and location defined, I can just write down this formula. Mass per unit area, the mass on each little piece of area is going to be the area times the mass per unit area at that location where that area is. So this expression here is just a way of calculating whatever we're interested in on that little piece, and then I need to add up over all the pieces. We're adding up over a surface, so this is called a surface integral. Everybody good? Again, I emphasize this is a very different kind of a Riemann sum, as I've got it written down here. This is not the same as a two-index, double integral Riemann sum. This is importantly different. Okay. Again, I'm going to call this a scalar surface integral because there's a different kind of integral that has a different kind of integrand and a different kind of differential that are going to come along later. So, and I don't want to talk about what that's going to be, but we'll need to distinguish between the two. So I'm going to call this a scalar surface integral. By the way, cultural point. Out there in the real world, outside of Math 212, pretty much people use the term surface integral and just it's understood that the context should make it perfectly clear. I mean, why should I have to say scalar surface integral? Look, you can see right there, it's a scalar, right? I mean, it's no one ever talks like that. But I think as we're developing these ideas, it's convenient for me to be able to refer to these specific constructions, and I need that distinction, scalar surface integral. Okay. Notation, well, again, little piece of surface area, delta S. We're going to shorthand that with ds. This summation happens over an area. It happens over, you can see that when you chop up an area, there's sort of two indices. There's the index that tells you how far you are along in that direction, and there's a separate index that tells you how far you are along in that direction. It's going to be a two-index summation ultimately. So we're going to use two integral symbols in recognition that there are two indices in the summation. Or if you prefer, that it is a two-dimensional domain. Okay. Details aside, though, this just says chop it up, add it up, just like all of our other integrals do. Okay. All right. So, for example, and again, there's lots of different examples that you could do. We talked about mass. On each little piece of mass is density times area. The total mass is the sum of all the little bitty pieces of mass, and therefore this scalar surface integral will compute for you the total mass. If only we could figure out how to compute that scalar surface integral. Okay. How did we compute scalar line integrals? Oh yeah, right. We did a pullback through a parameterization. Lucky break. It just happened to be that we had this existing idea of a parameterization, and curves were images of parameterizations. Good news. Same's true for surfaces. Right? I mean, now these kinds of parameterizations are a little bit different looking. There's two input parameters. These give position in space as functions of u and v, not just t, right? But nevertheless, we have talked about parameterizing surfaces, which makes the surface an image. Being as it is an image, we can talk about pulling back an integral defined on the surface, which we don't like because it's hard to deal with, it's dimensionally awkward. We can pull that back to an integral defined on whatever our pullback domain, which we do like because, this is a happy little story right here, right? It's a two-dimensional domain in a two-dimensional context, and it's just double integrals, and we've got all sorts of techniques. Okay. All right. So again, that's going to be the strategy, is to take a parameterization and think through how does the pullback work, just like change of variables. Whoops. Okay. Again, we're chopping it up into little pieces. Each little piece of area over there is going to have as its image a little piece of area over here. I need to know how much area that is on that little piece, because that's very important to how the Riemann sum works, right? On that little piece of area, I need to multiply density times that area, right? Not this area. That's the mass is over here. The mass is not in my pullback domain, right? So I need to be able to compute that area, ds. And this is going to look a lot like a calculation we've already done, by the way. Y'all remember with change of variables, right? We argued that, here we go, you can understand this little piece of area by understanding its edge vectors. Those edge vectors represent changes in the output, and they are changes in the output that come from, corresponding changes in the input over here. So I'm just going to write down what are these input vectors that sort of define that rectangle in my pullback space. I'm going to apply the derivative transformation, and from that try to deduce what are these vectors in the output space. And once we know those edge vectors, once we know these output edge vectors, now it's just a matter of using geometry to figure out if you've got two edge vectors, and if you've got a piece of surface which is approximately that parallelogram defined by those two vectors, then we use chapter 1 techniques to figure out the area of that parallelogram, which is again approximately the area of the piece of surface. Everybody see the strategy? Everybody notice how this is just like what we did with change of variables. All right. Okay, so here we go. These output vectors. Let's see, here we go. Yep, those output vectors, they are what comes out when you put in, why did I erase them? These output vectors are what comes out when you put in these input vectors. And these input vectors are kind of easy to write down. Here they are. And let me zoom in so we can see them better. But these input vectors, that one right there is E1 du, right? It's going in the direction of the u-axis, so that little width there is du. It's in the E1 direction. That vector is E1 du. Likewise, this vector here is E2 dv. So I'm going to take those two vectors, E1 du and E2 dv, and I'm going to plug them in to the derivative transformation. And again, the derivative transformation takes input vectors and gives me output vectors. So just like we did in change of variables, just like we did for scalar line integrals, we now just kind of go through and plug and chug. And the algebraic analogy is, I think, very strong. Notice these are scalars. They'll just factor right out. What we're left with here, linear transformation applied to standard basis vectors. Those are partial derivatives. So, nice, convenient formula. You'll even recognize, xu du, xv dv. We wrote exactly that down when we were doing change of variables. It's morally equivalent to the result. So, there is one difference here. When we were doing change of variables, we were looking at input vectors that gave output vectors that were also in the same dimension. There was R2 to R2 when we did this, right? These were two-dimensional vectors in R2, and I wanted to compute the area of a parallelogram. And there was a certain formula for that in R2. Just determine it. Make a matrix, do the determinant. Okay. These are now vectors in space. And so we have a different formula. Let me show this picture. Different formula for the resulting area. So we just got through computing these two edge vectors, xu du, xv dv. We want to compute this area. And the formula for the area is that area is the length of the cross product. So I'm just going to write down length of the cross product of these two vectors, xu du, xv dv, and compute. Here's how that calculation goes. Again, those edge vectors I just computed, xu du, xv dv. Area is the length of the cross product. Scalars factor out. This scalar factors out there. This scalar factors out there. And notice all you're left with is this weird little formula here. But the length of the cross product of the partial derivatives of the parameterization. And as we wanted, this gives us area of the output piece as a multiple of area of the input piece, du dv. So said differently, this is our stretching factor. How are we doing? Everybody on board? So, by the way, I think a really healthy exercise, and I want to encourage everyone to think about doing this, really healthy exercise would be to go back to the change of variables section and then kind of compare and contrast. Look at, okay, well, we did that there, we did that here, and oh my gosh, the similarities are going to be very, very strong. Different result now. This formula, hey, what happened to the determinants? If this is so much like change of variables, how come that's not a determinant? Well, I've got two vectors in three-dimensional space. It's just a different geometry. Similar though it is, it's not exactly the same. the different geometric context means you've got to apply a different geometric formula. By the way, even if you wanted to blindly just plug in this into the determinant formula anyway, it's not going to even make any sense, right? You've got two three-dimensional vectors. That corresponding matrix isn't even square. Determinant isn't even defined. So that makes no sense at all. So definitely don't do that. Okay, so we're all set. Here, a little bit of notation before we celebrate. This vector here is very useful. This vector is going to come up a lot. Let's see here. Let me use orange for this. This vector xu cross xv. That vector comes up so often. Has such nice features. We're going to give it a name. We're going to call that capital N. I emphasize capital N. The capital N in this class is going to be our sort of indication that this is not just some random normal vector. This is specifically the normal vector that comes out of the parameterization and whose magnitude, whose magnitude, if you look at the magnitude of that magnitude is our stretching factor. Right? Anyway. So in other words, capital N is this very specific normal vector, and again, going forward, that's going to be useful. Okay, so that said, here's our formula for how to compute scalar surface integrals. If you find yourself, for whatever reason, wanting to add up, some sort of an accumulation, maybe you're chop it up, add it up on the mass on some surface, or chop it up, add it up on the number of, weeds growing on a hillside, whatever. The way you compute a surface integral is pulling back through a parameterization. Whoops. So x parameterized in terms of u and v. ds. ds is all of this business. Namely, it's a stretched, sort of a stretched out version of what went into it, namely du dv. Notice that everything in that computation comes from the parameterization, right? This thing right here, this is literally plugging in the parameterization. This stretching factor is a magnitude of a cross product of partial derivatives of the parameterization. So again, everything in this integral on the left comes from the parameterization. And having pulled back through the parameterization, we have an integral that's all in terms of u and v. The pullback domain in the uv plane, double integral, plain old, section 5.3 style double integral. Okay, so examples. So let's suppose we have a metal sheet. Now I'm going to do a metal sheet, no particular reason. We've got that application already agreed upon. Metal sheet with a, density as a function of position. We know that mass is computed with this scalar surface integral. Okay, so details though, how are we going to actually compute that thing? Well, step one is to parameterize. Right, again, you can see it right here in the formula. If you want to pull back, you've got to parameterize. You've got to parameterize your surface. So how do we parameterize our surface? Let's look at our surface, by the way. The surface is a graph. Keyword. It's the graph of this function. So let's interpret that with an equation. What does that mean? This is a graph of that function, our equation has this surface. Our surface has this equation. Sorry. Z equals x squared plus y squared. That's what graph means, right? Right. Okay. How do we parameterize Graphs, well, my favorite technique for parameterizing surfaces is graph parameterization. And here it is, right? The graph parameterization technique says take your input variables x and y, and just let those be u and v. Keep in mind, by the way, when we say we're parameterizing means we are writing x, y, and z as functions of u and v. So these input variables x and y, setting them equal to u and v means those are the first two components of our parameterization. Everybody good? Okay. What is the third coordinate of the parameterization? Well, you don't even have a choice in the matter. You kind of have to do what you kind of have to do. U and v are x and y. You plug that in there, that tells you what z has to be. Right? We're looking at a graph. So this is what z is, and having plugged in that x is u and y is v, that means that z has to be that. No choice. How convenient. And anyways, there's our parameterization. We have x, y, z as functions of u and v. Make sure you're good with the graph parameterization. It comes up so much. It's, the graph parameterization and its coordinate system alternatives, spherical graph parameterizations, etc., are almost always how you're going to parameterize, at least in this class. So make sure you're good with that. Why did I erase that? So so there's our parameterization. Now go back up to our formula. How am I gonna do the pullback? Well, I've got to compute my stretching factor. My stretching factor is kind of a pain. I've got to take my parameterization that I just found. I've got to take partial derivatives with respect to the two input variables. Then I've got to take that cross product, and then I've got to take this magnitude of that cross product of those partial derivatives of that parameterization. Right, so multi-step process. So let's go ahead and do that. Here's that parameterization again, and here you go. Formula for the stretching factor. Parameterization is that. Partial derivatives give you that. Now that's just computing, right? That's straight up partial derivatives. Super easy. World's easiest derivatives to compute. Needing to compute now the magnitude. Oh, excuse me, I got to take the cross product. Got ahead of myself. Got to take the cross product there. Again, got to make sure you know that formula, but it's just a formula. You just, plug and chug, write it down. And then having done the cross product, now we have to take the magnitude of that cross product, and that gives you this. So there's your stretching factor. It's a kind of an ugly little formula, but there it is. Everybody see how that works? Straight out of the parameterization per a complicated formula that we motivated. Okay. Yeah, so now it's all plug and chug. Let's see here. Yeah, so our parameterization, position as a function of u and v, there it is from the previous page. Density was given as a function of position, like so. Now let's remind ourselves. Density was given as z squared. Density is z squared. So coming down to here, you can totally see that right here in the formula. I'm going to take this z and square it. You ready? See what I'm doing there? Okay. Let's see here. What is ds? The area on the little piece of surface. That area is stretching factor. that we just computed times dA times du dv, that is. So all I did, I'm just emphasizing with the colors here, all I've done is just follow the formula, just plugging in. And as a result, we get this integral. And it's a little ugly of an integral. Let's talk about the domain for this integral real quick before we go on. The domain for that integral, we've got to think about the parameterization here. We parameterized with this formula by thinking about the fact that our surface is a graph. So the range of values, let's see here, what is our domain? U and V are going to range how? Well, don't forget what U and V are. U and V are X and Y. So if you want to know what's the range of values of U and V, you just need to figure out, well, what's the range of values of X and Y on our original thing? And on our original thing, we're looking at the part of the graph of this function sitting over the unit disk in the XY plane. And so because we're over the unit disk in the XY plane, X and Y range over the unit disk, therefore U and V range over the unit disk. And of course that's the unit disk in the UV plane. Everybody follow that reasoning there? That's another really nice thing about the graph parameterization is you can kind of just read the domain straight off of the statement of the question, making the appropriate connections. Okay. All right. So we have a integral over the unit disk. By the way, this looks like a monster integral. There's a square root right there that I'm not looking forward to. It's part of my integrand. Worse, this domain is a circle, which means that there's going to be square roots in my bounds, which will, after I do my inside integral, I'm going to have more square roots in my integrand when I get to that last outside integral. And so this looks like a death by square roots. Anybody have any clever ideas of how to avoid all of that pain? Got a good suggestion here. Use polar coordinates. Okay, so let's think that through. What happens with polar coordinates here? Keep in mind our domain is the unit disk. And the unit disk, it's got all sorts of square roots in the bounds if you do it in rectangular coordinates. But if you use polar coordinates, the unit disk, constant bounds. Theta goes from 0 to 2 pi. Right? R goes from 0 to 1. Constant bounds. And a lot of those square roots just kind of go away. Furthermore, you'll notice that this becomes just r to the fourth. This simplifies a little bit as square root of 1 plus 4r squared. Du dv becomes r dr d theta. Right? So it's still, it's not, could be better. I've seen easier integrals, but this is not that bad, and a clever substitution will crush this integral. Everybody on board? Okay. So that'd be a good one to think through. Think through how to crank out that resulting integral with polar coordinates. Okay. All right. Okay. Let's see where we. All right. So another example here. I'm going to let y'all read this example as well. I think this is a fun one, and works out interesting kind of a result there. Okay. Details for y'all. Exercises. And we're going to move on to section 510. This is a really quick section. I need to introduce a new kind of mathematical object. I've already kind of made vague reference to where I'm going to need this object. You may recall I was talking about line integrals and surface integrals, and I made the observation that we've got to distinguish those specifically as scalar line integrals and scalar surface integrals. Because there will be another kind of line integral and another kind of surface integral. The integrand of these new kinds of integrals that we're going to start working with tomorrow. Now think about it. The integrand is going to be something called a vector field. So I've got to be able to tell you what a vector field is so that we can do business with vector fields we're going to define a line integral over a vector field. And we're going to define a line integral over, a surface integral of a vector field as well tomorrow. Okay, so what is a vector field? We've actually seen a bunch of examples of these kinds of things in the past. Here's I think a natural sort of first vector field to see. This is a picture of what gravity looks like. Right? So imagine the Earth like that. There's our little blue marble. Right? And y'all know how gravity works, and if we were here, we would feel a force of gravity toward the Earth. And we represent forces with vectors. No surprise. That's all chapter 1. Forces are vectors. Okay. We also know that if we were over here, well, that's farther away, so the gravity will be less. It's still pointing toward the Earth, but we're in a different location, so that's also a different direction. And so that force would be represented with that. Again, a vector. And again, chapter 1, right? I mean, forces are vectors. No news there. So what is this mysterious new thing, the vector field? The vector field is just the recognition that there is a vector at every point in space that describes the corresponding force of gravity. It's, in some sense, you might say, all of those vectors kind of collected together. Be one way to think about it. So this whole thing is called a vector field. And sometimes people will, it's a little sloppy, but sometimes people will just say a field. By the way, there's another mathematical object called a field that is very different. It's not going to come up in this course. Anyway, in this context, the word field means vector field. In other contexts, be aware the word field might mean a different thing, but anyway. Okay. So, yeah, vector field, this is the vector field representing gravitational forces. So, gravitational forces, and so combining this long statement into something a little bit more convenient, gravitational field. Y'all ever heard the term gravitational field? That's all they're talking about, right? It just means the vector field representing all of the vectors, representing the forces, the gravitational forces at those locations coming from the Earth. So this is the Earth's gravitational field. Okay, so in general, though, a vector field just means a bunch of vectors at different locations. All right. So now, before I go on, some of y'all may have had an E&M course. Out of curiosity, and it doesn't really matter, but how many people have had an E&M course? Not very many. Okay. All right. For those of you who have not had an E&M course, there exists something called an electric field. An electric field, highly analogous. If instead of this representing a planet, if this were representing a charged particle or a charged mass of some sort that has an electric charge, some sort of buildup of electric charge. Turns out electric charges create forces. It's kind of like gravity. The formula is surprisingly similar to the formula for gravity. Like charges repel each other and opposite charges attract each other. That's just the way the world is built. And you can write down formulas, and the picture of the resulting vector field looks a lot like this. And so if this were a charged particle, then the resulting vector field representing the electric forces from that charged particle, we would call it, you've probably heard this expression as well, the electric field. It's very, very similar. Okay. All right. There's also something called a magnetic field. It's importantly different, but it's still a vector field, just not in this way. That doesn't represent forces. Magnetic fields are weird, but that's this is not a physics class, so we're gonna leave that aside. Okay, now I think forces are a useful metaphor for seeing vector fields. It's very physically relatable. We all walk around on planet Earth experiencing this vector field of gravitational force every day, right? And we all understand that if we go into the southern hemisphere, we don't fall off. So we understand that gravitational forces are directional, depends on location, and we have a pretty good experience for this. Okay. It is not the only good metaphor for vector fields. There's another really important metaphor for vector fields, and again, there's more than this as well, but fluid flows. So I'm going to distinguish this from a vector field representing forces. I'm going to call this a flow field as opposed to a force field. Not, no relation to science fiction, ray gun, force field, not like that. So a flow field just represents how fluids are flowing. For example, this. Maybe you've got a pipe, and at any location in that pipe, there is a vector representing the velocity of the fluid flow at that point. And at different points, closer to the edge, for example, you're going to have a different velocity. Velocities are represented with arrows, vectors. And so, one at a time, a vector can represent how a fluid is flowing at that one point, right? But if you want to talk about the flow overall together as a whole, you need all of the vectors, and so a vector field, again, is the perfect tool for that. Vector fields represent how fluids are flowing. So here I have fluid flowing through a pipe. Maybe here I have fluid that's flowing on top of a bucket, and I've sort of stirred the bucket of water, something like that. Yeah, everybody okay? All right. FYI, we're going to do a bunch of we're going to solve a bunch of real world problems. I'm going to say physics, right? But we're going to do a bunch of sort of, engineering / physics kind of problems. And some of the problems that we're going to do are going to involve forces. And some of the problems that we're going to do, very importantly, are going to be about fluids, not forces. So the warning I want to give you right now is some students sort of make the decision, I'm just more comfortable thinking about fluids. I'm going to go through Math 212 where every vector field that I see, I'm going to just visualize that as in terms of fluids. That's not going to work, right? You've got to have to also be able to think about forces, and vice versa. If you find forces more conveniently relatable, and you want to hang your hat on that and never think about vector fields from the point of view of fluids, again, mistake. That's not going to work. We're going to have some applications that unavoidably have to be thought of in terms of fluids. So, anyway, keep that in mind. All right. Okay, so there is a special kind of vector field I want to point out, and this is just kind of a passing comment, but suppose you have a real valued function. Now think back to chapter 4. So real valued function, so function with real number outputs, but a function of several variables, so multiple input variables. So the domain is Rn. We know how to compute the gradient. Right, we have a formula for how to compute the gradient of such a function. The gradient, y'all remember the notation, and y'all remember that it is a vector. And what have we done with gradients so far? Well, we've looked at gradients at single points. And at that one point, we consider, the gradient does a certain thing. It points, it has, the direction has a certain interpretation and blah, blah, blah. 1 point at a time. So now let me just extend that concept to, don't forget we get a gradient vector, one for each point in the domain. And so in fact, the gradient overall is actually a vector field. Right? So here's an example. Here is a real valued function of two variables. Right? So real valued, two input variables. And here's the very familiar formula for the gradient. Y'all remember how to compute gradients? And check it out. It's a vector field. At every different point in the domain, for every point in the domain, x, y, for every point in the domain, I get a formula here for how to compute that vector called the gradient vector. And it looks something like this, sort of radially outward. And let's see, so at a point, for example, there, at that point, the corresponding vector is like this. Everybody on board? By the way, a quick observation. Notice in this formula here, I could rewrite this formula as that this gradient vector is 2 times the position vector x. Here, let me do that in green. 2x. So the gradient vector is 2 times the position vector, and you can see that in at least my attempt here to draw the geometry of this picture. Oh gosh. So the gradient vector is just a multiple of the position vector describing my location. Everybody good? All right. Sadly, we are out of time, and I did not get to where I wanted to, but oh well. We will pick up here on tomorrow, which is Friday. And we did not get far enough into 5.10 for me to be able to include 5.10 on the fair game material for the exam. So the fair game material for the exam will be through section 5.9. And I'll send out an email to that effect this afternoon. Okay, see y'all later. Oh, and I do have homeworks to return if you'll stick around for a moment.